Hey there, welcome to this explainer. Grab your notes, maybe a cup of coffee, because today it's literally just you and me tackling some of the toughest topics in your algebra and sequence revision. Think of this as our own focused, one-on-one study session to crack those notoriously difficult exam questions together. We've got this.
Okay, let's jump right in. Be honest, does this notation make your head spin? Trust me, you are absolutely not alone. It's completely normal to feel a sudden wave of panic when you flip open an exam paper and see symbols that look way more like a scary foreign language than anything resembling math.
But hey, take a deep breath. We are going to crack these formulas together. I'm right here with you, and we're going to dismantle these daunting questions piece by piece. We'll start with the mechanical stuff, decode that crazy notation, and figure out exactly what the exam is actually asking you to do. Because once we break down the patterns, it's really not as terrifying as it looks.
All right, first major hurdle. Let's demystify algebraic long division. Yeah, the infamous bus stop method, but for polynomials. It looks incredibly complex when you have, say, 5 terms with powers of x all lined up waiting to be divided, but it really just boils down to a very simple, repetitive loop.
Here is exactly how that loop works in 3 simple steps. First, you just divide the leading term. So if you're dividing an x cubed expression by x plus 2, you just divide the x cubed by x to get x squared. Boom. But here is the absolutely vital point. Step 2. You must multiply back to adjust. Because you only divided by the x and kind of ignored the plus 2, your initial answer is only a partial division. Multiplying back corrects that error. Finally, step 3, subtract the 2 expressions to see what's left over, and then you just loop back to the start and repeat it for the remainder.
Now, what's the ultimate point of all that looping? Why are we even doing this? Well, if you get all the way to the end and your remainder is exactly 0, congratulations, you've successfully proven that your divisor is a true factor. But if the remainder is literally anything else, say a negative 20, then it's just not a factor. It really is that black and white.
But what if the exam doesn't even give you the factor to start with? Okay, here is a massive insider exam tip. Instead of randomly guessing factors and wasting 20 minutes on a long division dead end, just plug values directly into the equation. If you substitute all the x's with a 2 and the whole equation equals 0, then x minus 2 is a guaranteed factor. Test a few small numbers, find the 0, and only then start your algebraic long division. It's an absolute game changer for saving time.
Okay, let's pivot a bit. We have survived long division. So let's tackle another area that trips literally everyone up. Decoding tricky sequence notation. I fully admit, the notation here is basically designed to look intimidating. It's almost like they want to test your nerve before you even start the actual math. So let's demystify it right now. Have you ever seen a lowercase u with the tiny n next to it? People overthink this. That little n is just a placeholder symbol. It simply tells you the exact position of a term in a sequence. It marks the nth term. So if your sequence rule says u4, it just means you're looking for the 4th number in line. That is all there is to it. And then there's this beast, the capital Greek letter sigma. It looks super intense, right? But sigma is literally just the Greek letter S, and S simply stands for sum. It's just a command from the exam paper telling you to add the terms of the sequence together. The little number at the bottom tells you exactly where to start adding, and the number up top tells you exactly where to stop. It's literally just a strict set of instructions.
So, now that we can actually read the instructions, let's apply them. Let's move to geometric series, specifically looking at infinity. Now, in an arithmetic progression, we add or subtract to get the next term. But in a geometric progression, every term is multiplied by a common ratio. And that brings up a really fascinating concept.
Specifically, how do you add to infinity? It sounds like a trick question. How can you possibly sum up an infinite number of terms without the total just blowing up into some infinitely massive, incalculable number?
Well, think about it like this. Imagine a sequence made of fractions. Say your common ratio is 1/5. Every time you multiply your sequence by 1/5, the fractions get smaller and smaller. By the time you do this hundreds of times, they shrink until they are infinitely small. When a number becomes essentially 0.000001, adding it to your total makes almost zero difference. It practically vanishes.
And this brings us to a magic shortcut, the sum to infinity formula. S to infinity equals a divided by 1 minus r. Here, a is your first term and r is your common ratio. Because those terms at the very tail end of the sequence become infinitely small, we can just completely ignore them. It's brilliant. This beautifully simple formula takes an impossible infinite calculation and turns it into a basic division of fractions.
All right, study buddy warning flag time. Red alert. We've got the formulas down, but the exam board loves to set traps. We need to talk about avoiding common calculation errors, because honestly, nothing is more frustrating than doing all the complex algebra perfectly, only to lose points on a silly basic arithmetic slip. So, keep these 3 traps permanently etched in your brain. Trap number 1, BIDMOS errors. If your geometric formula asks for 4 times 5 to the power of 3, you absolutely must apply the power first. 5 cubed is 125, and then you multiply by 4. If you accidentally calculate 4 times 5 to get 20 and then cube it, you'll get an insanely wrong answer. Trap 2, double negatives. If you're subtracting a negative remainder in long division, you are actually adding. Missing that flips your whole result. And trap 3, confusing geometric and arithmetic rules. Always stop and ask yourself, wait, are we multiplying to get the next term or adding? Identify your common ratio or common difference immediately before doing anything else.
Okay, home stretch. We are in the final part of our revision session now. Let's focus strictly on the rule-based algebra of logarithms and surds. Honestly, if you love clear, predictable rules, you're actually going to really enjoy this section. First off, let's translate the concept of a logarithm into plain English. A logarithm is essentially just working backwards from a power. It just asks the question, how many times do we multiply the base to get the target number? So log to the base 2 of 8 is really just asking, hey, how many 2's multiply together to make 8? The answer is 3. Oh, and if you ever just see log written with no base number at all, the universal rule is that we always assume the base is a 10.
Now you might want to grab your phone and snap a quick screenshot of this cheat sheet. These are your golden rules. Notice the logic here. If you're adding 2 logs with the same base, the shortcut is to secretly multiply their target numbers together. Log 2 plus log 7 perfectly simplifies to log 14. If you're subtracting them, you divide. And the rules for surds operate in a really similar way. The square root of a multiplied by the square root of b is simply the square root of a times b. So root 2 times root 18 just becomes root 36, which resolves beautifully into a clean number, 6.
The crucial takeaway here is that mastering these foundational rules gives you the ultimate toolkit to dismantle almost anything the exam throws your way. But I want to leave you with a little challenge to test what we've reviewed today. Think about these 2 tricky edge cases. What happens when you encounter a log to the base of itself, like log base 5 of 5? Or, based on what we just learned, what happens if you try to take the square root of a negative number using our surd rules? Really think about the underlying logic we just unpacked. I highly encourage you to apply these rules and see if you can solve those trickier edge cases on your own. Keep practicing, trust the structure we built today, and you are going to absolutely crush your exams. You've got this.